Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all in my today class. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. Uh, Class, we are starting new unit, the nuclear physics. It's unit 19, and the topic is mass defect and binding energy. Students, this is very unfortunate, as I told in my previous class also, that because of the COVID-19, the syllabus has been reduced, but the reduction in syllabus is problem for us. Why? Because that directly starting to mass defect and binding energy wouldn't be that much effective. This is why, since we have time also, so this is why I thought it wise to just give you a brief introduction before going into the mass defect and binding energy. This is why I intend to divide this into two parts, mass defect and binding energy part 1, and mass and in my next lecture 53rd I will teach you mass defect and binding energy is part 2. In the part 1 I will emphasize more on the introductory part and less on the binding energy part, right? So maybe inshallah you'll be able to touch the mass defect at the end of this. So let us start with our topic. The first topic is the introduction to the nuclear physics. That what is nuclear physics? So here I would like to tell you about the nuclear physics. That what is nuclear physics? In the nuclear physics, we are going to study about, in nuclear physics is the study about the study of the structure, about the structure and properties of what, and properties properties of nuclei. Nuclei is the plural of the nucleus. Properties of nuclei, nuclear reactions, nuclear reactions and their applications in our daily life. This is what we will study in the nuclear physics. So the main focus of the nuclear physics here is about the structure of the nucleus, right? And then the properties of the nuclei, that what are the properties of the nuclei, about the nucleons also, and then we will study about the nuclear reactions also. And you know, these nuclear reactions are two in number. There is the fission reaction and the fusion reaction, and their application in our daily life, both in the time of peace and war. So what is nucleus? Nucleus is in fact the it is the central, highly dense, highly dense and the positive charge part, and the positive charge part of the matter, of the atom. right? And it was discovered by Rutherford. You already know about its discovery. Now, few things I would like to tell you here about. And beside, I'm coming to this point that we will discuss here the nucleon, nucleons, nuclide, sorry, the size of the nucleus, right? The mass and charge number, mass, charge number, atomic mass, and atomic mass unit AMU, and atomic mass unit. This is what I will explain to you here. Okay, now let us see. This is what you can say that look at the periodic table as I told, and here you see in this periodic table, look, if you just choose, let us first choose any, for example, any element, and if we choose hydrogen as you see here, look, for this hydrogen you see that this is what, this is the symbol of a particular element. This represents this whole, this is the symbol. And here you see that this is what we call, if it denotes in the nuclear physics, this whole is called as the nuclide. Nuclide is rather a single nucleus. Okay, and here this is, this part we call it the charge number part, the charge number, that is the number of proton inside the nucleus is the charge number. Here you see it is the mass number, mass number. Mass number is the number of nucleons together in the nucleus. And mass number, this is denoted by A. And mass number is the sum of the charge number and the neutron number inside the nucleus. So in one way, the number of neutron in the nucleus will be A minus Z. Now you see here, look, in this case here you see that, look, for certain, for example, for the isotope, usually for the isotope, the mass number, the charge number Z never be the same for what, for the neutron number. For example, like isotopes, okay, for them or for heavy nuclei, that Z never equal to N. So for some element, the N by P ratio, yeah, the N by Z ratio is 1. These are usually stable nuclei. They do not radiate, stable nuclei. We call them the stable nuclei. And for all those elements in which the N by P ratio or the N by Z ratio is not equal to 1, they are usually unstable and are radioactive in nature. So this is what the nuclide is. So nucleon is the particle that are found inside the nucleus. So the number of neutron and proton together is called the nucleons inside the nucleus, and we call it the mass number. So mass number is the sum of proton and neutron inside the nucleus, while charge number is the number of the charge number is the number of proton inside the nucleus. Mass The neutron number and the charge number are not necessarily to be the same. As I told, for stable, yes, but for unstable, no. But in the charge number and the number of electron, we usually denoted this by uh, number electron, by either number of electron inside the an atom is the same as the number of proton if the given atom is neutral, right? So here you see this, the mass number. Clear? Okay, now another important point, one is the atomic mass unit. Here you see the atomic mass. Okay, the atomic mass unit, AMU. There is a difference between atomic mass and mass number. Mass number refers to the number of particles inside the nucleus, while atomic mass is the mass of those particles together are called the atomic mass. So that are important about this. Now let us start for the as I told about the nucleon to you, about the nuclide also. Now let us talk about the size of the nucleus. Now as I told you that the, let us for example, if we have this as the, let me make it a nucleus here. This is nucleus with this as the diameter of the nucleus. This is the entire diameter, the diameter of the nucleus, diameter of the nucleus. Now let's see that this is the F, I denote it by R. This is the radius of the nucleus, and I denote this radius by R. Right? Experiment reveals that the not all of the atom have the same radii. Experiment shows that the radius of the nucleus, you must remember this might be your MCQs, it is directly proportional to the cube root of the mass number, right? That R is directly proportional, the radius, to the mass number. Oh, sorry. Like that. R, this R, the radius of the nucleus, is equal to R naught, which is constant, and that is the first Bohr radius. And this R naught is equal to 1.2 into 10 raised to the power minus 15 centimeter, right? Or you may say that this is 1.2 into 10 raised to the power minus 17 meter. This is the radius of the nucleus. Okay, so now look, if I just use the hydrogen, then it could be this one. So this is extremely small, but beside this, as I told, that it is the central. Why? Because it occupies the core place. For example, the matter, and then you come to the molecules, then you come to the atoms, and then you come to the nucleus, where molecules is a group of atom. An atom consists of the nucleus and an orbiting electron or electrons, while nucleus is the central. So it occupies the core place, and it is highly dense. Why the highly dense? It is the highly dense because that, as I told, that nucleon, they could be either proton or they could be either neutron. And you know that the mass of the proton is, the mass of the proton is 1836 times then the mass of what? The mass of one electron. So, and similarly, the mass of the neutron is nearly equal to the mass of what? To the mass of the proton. So now, for example, if you just take helium, look into the helium nucleus. So here, for the helium nucleus, what do you see? Look, you have two proton and two neutron. So four nucleons you have. And now look, if you multiply this number with a 4, right? So the mass of the entire nucleus will be 4 times this number, right? So this is why, since the mass of the electron is extremely small, therefore the entire mass of the matter is concentrated at the nucleus. So for example, if I just zoom the atom to the size of the earth, then the nucleus will become to the then the nucleus will become the size of the tennis ball, and still it will be heavier than the rest part. So this tells that how much dense it is. Now the positive charge part, since you know neutron carry no charge. Neutron has mass while it has no charge, right? While proton has mass also and it has charge also. So this is why I told that it is the positively charged part of the matter. So that is all about the size of the nucleus, that the structure and the size of the nucleus, that the size of the nucleus is proportional to a cube root, the a power 1 over 3, 1 over 3. Okay, so now let me tell you something about the this is what I told about the mass number. I explained the mass number to you, that this is a mass number and this is the atomic symbol, as I told, that represents the symbol, and as I told, in the nuclear physics we usually call it a nuclide. Okay, the atomic number and the mass number, the number of proton is actually the atomic number. I told the number of electron equals to the Z when the atom is electrically neutral. This is what I told you in the beginning also. This is what about the mass number I also told, and the number of neutron and the number, and that is the number of neutron, the neutron number, as I told, n equals a minus z, right? And this is what I already explained to you, the point which I want to come to. Now I'll be explaining that to you. Now the atomic mass unit, since you know that, let us see here, for example, if you see to the mass of what? The mass of the electron, the charge number, it is Az, this is Az, this is Az. Let us talk about the mass of the electron. You already know the mass of the electron is 9.11 into 10 to the power minus 31 kilogram. The mass of the proton is 1.6727 into 10 to the power minus 27, and roughly neutron has the same mass. Now you know that, and these masses are what? These masses are extremely small masses. They are what? And they are extremely small masses, and this is very we cannot say difficult, but to some extent to deal with such extremely small numbers. So to make our calculation easier and meaningful, we usually use the atomic mass units. Now, what are the atomic mass units? The atomic mass units, the mass of an atom in gram is very small, as I told, and not very useful because the samples of the matter that scientists work with contain trillions of atoms. So this is why we cannot use it for experimental purposes. In order to have a convenient way to compare the masses of atoms, scientists choose one isotope to serve as a standard, because for everything we choose a standard for our measurement. Like for example, to measure length you choose meter is the standard. So here you also choose the atom, the isotope of a certain or a particular atom, that is carbon, is the standard. So scientists assigned 12 atomic mass units to the carbon atom, which has 6 proton and 6 neutron. So an atomic mass unit is defined as, this is important, atomic mass unit, it is defined as what? Atomic mass unit is defined as the 1/12 of the 1/12 of the mass of the carbon atom. It is 1/12 of the mass of the carbon atom. So now look how it looks like. There is the this comes out to be, look, one atomic mass unit is equal to 1/12 the mass of the carbon atom. Since one carbon atom has mass 12 gram, or you can say 12 into 10 raised to the power minus 3 kilogram. So, and one mole of atoms have contained these many atoms. So one atomic mass unit, 1 AMU, then equal to 1/12 into 12 gram per mole, because in 1 mole it has this one, and 1 mole divided by, and how many particles we have in 1 mole? We have 6.022 into 10 to the power minus 23. This is in 1 mole, right? So that is what will be the mass of one such particle. So it will be 12 gram, one such atom, 12 gram divided by what? 12 gram divided by this number. So it will come out to be 1.66 into 10 to the power minus 27 kilogram. So here you see that the mass of one, electron then comes out to be 0.00549 using this, the mass of the proton like this, and the mass of the neutron like this. This is very easy. Let us see here. Look, is one atomic mass unit is equal to what? One atomic mass unit equals 1.66 into 10 raised to the power minus 27 kilogram. So here you see that 1 point log. So what does this means? This means that 1 kilogram will be equal 1 over 1.66 into 10 raised to the power minus 27 uh, atomic mass unit. Now look, for example, if you want to do this for the electron, so let me do it or finish my calculation for electron. So multiplying this number on both sides since it is in kilograms. So what will be the mass in the atomic mass unit for an electron? It will be 9 multiplying both sides by this 10 to the power minus 31. So it will came out to be 9.11 into 10 to the power minus 31 and divide by 1.66 into 10 to the power minus 27 atomic mass unit. So if you use your calculator, it will come out to be this number. One is this thing. Similarly, beside this, we also use the another equivalence, and that is that one atomic mass unit is equal to this. So we also use uh, the that is the masses in term of energy. E is equal to what? mc square. So the mass of what? The mass of the this one, for 1 kilogram mass, the energy associated with 1 kilogram mass will be equal to what in term of MeVs? You can now put this, right? Or this one here, mass in kilogram, the value of C, this you will get the answer in joule as I did, and then convert the joule into electron volt. Similarly, you can just calculate the masses in term of energies also. Okay, so this is how the atomic mass the atomic mass units are in. Definitely throughout this chapter we will be needing this thing. Particularly we will be needing the atomic mass of the hydrogen, the helium, and to the least carbon and nitrogen. This is what I will just do this, but this is what mostly in our calculation we will be using this. We will be using uh, this one okay, and date of the nutrient also mostly we will be using this one. Now let us come to the mass defect. That what is the mass defect? Mass defect, this is one of the most important scenario here. Is that if you just see, look, I want to tell you that the mass of the nucleus, the mass of the nucleus, mass of the nucleus is always less than the mass of the is always less than the mass of the sum of the constituents of that nucleus, of that nucleus. This is very easy. For example, look, uh, take for example the example of the helium 2 4. Now let us see that the question is, for example, if I tell you that I have a pen in my pocket and the pen has mass, for example, 10 gram. Okay, if I tell you that if I remove the pen from my pocket and if I uncap the pen, then the mass, for example, if this is the mass of the pen in my pocket. Now, once when I open the cap of the pen, then cap plus the rest part, I would call that cap of the pen and pen. The rest part, when I add them together, it came 12 gram and here it came 10 gram. No one is going to believe this thing, as it is against the law of conservation of what? Law of conservation of mass. The same thing is happening here, that the mass of the nucleus is always less than the mass of the sum of its constituents, right? So where is the missing mass goes? That is a big question here. And that missing mass we call the mass defect, and that is in fact the mass which is destroyed when the nucleons are combined to form a heavy nucleus, and that mass is converted into energy. According to the Einstein famous mass energy equation, E is equal to mc square. So that is one of the reason. For example, here, look, you see that the mass of the helium nucleus, I will write here mass of the helium nucleus, the entire nucleus. And now you see that, look, how many the mass particles there? Look, there are 2 protons. So the mass of 1 proton multiplied by 2. And then there are 2 neutrons. So plus the mass of what? Plus the mass of 2 into the mass of what? Into the mass of 1 neutron. Now this must be the same, but here this tell you that no, they are not the same. The mass of the nucleus is not the same as the mass of its constituents here. And now let us see it, check it here, that how. Look, what is the mass of the helium? As I told, The mass of the helium is this one, 4.0026. 4.0026 AMU, atomic mass unit. And now look two, and what is the mass of one proton? As I told that you will most often need this thing. It is 1.007316. 1.00736, is it? 1.0073116. 16 plus 2, and what is the mass of one neutron? Let us see. That is 1.008701. 1.008 1.008701701. Now if you use your calculator, then look what this will come out to be. See here, if I use my calculator, let me tell you that what could be this number. 2 into 1.0073116 plus 2 into 1.0087001. So this came out to be 4.0320 32034, and here it is 4.0026. So now you see that they are not the same. And what is the difference? This difference will be equal minus 4.0026. This difference came out to be 0.029434. So this is in clear violation of the law of conservation of energy. No, sorry, mass. This difference, we call this as the mass defect. This is called what? This is called the mass defect, right? And this mass defect we denote by delta M, and I would write for the helium nuclei like this, 9434. Okay, so now you see that, look, as I told, a clear violation of the law of conservation of what? The law of conservation of mass. But where this missing mass goes, this missing mass appears in the form of what? Yeah, it destroys into what? Yeah, it transforms into energy. This is why, if you remember in the previous unit, I told that mass and energy can neither be created nor destroyed, but they are interchangeable. Interchangeable. That mass can be converted into energy and energy can be converted into mass. This is known as the mass defect. Remember, every element has a mass defect except hydrogen. This hydrogen, it has zero mass defect as what? For hydrogen, the mass defect for hydrogen, mass defect of hydrogen is 0, right? It has mass defect what? It has 0 mass defect. For hydrogen is the only element which has 0 mass defect. Why? Because it has no neutron in it. Okay, so now let us see how we can find this mass defect. The mass defect can be found, this mass defect, it can be found by calculating what? Calculating the combined mass Z into the mass of one proton plus N into the mass of one neutron, number of neutron into the mass of the neutron, minus the mass of the combined, yeah, the mass of the whole nucleus, right? or you can say that it will be Z into mass of proton plus A minus Z into the mass of neutron into minus what? Minus uh, the mass of the nucleus. This is the mass defect. So for hydrogen, you see that the number of, there is no neutron, so this will be Z minus MP, and then of course there is only one proton, so this mass defect will come out to be zero for the hydrogen. So mass defect plays a very important role in that. I will explain it to you that it is actually this mass which is changed in, which has been converted into energy when nucleons combine to form a heavy nucleus. And we will discuss this inshallah in the binding energy. So our second part to the first will be the binding energy, right? And the mass defect I explained to you, right? So inshallah, see you in the next lecture. Thank you very much.